I'm Dr. Creighton, and in this video we'll be discussing rational exponents. There's quite a bit here, but essentially the idea is you'll be able to perform algebra with both integer and fractional exponents, which behave very similarly. You're going to be able to convert between radicals and fractional exponents, back and forth, simplifying any radicals, so they're much nicer, so this is the beginning process of doing that, and then doing algebra with radicals, so like add, subtract, multiply, and divide. These are the properties that we'll be using in order to do these appropriately. We're going to start off here with simplifying the fifth root of x to the 15th, assuming that x is positive. The variables being positive is going to be a running assumption for many of these things, because that avoids the issue of principal and non-principal roots. It will just be all x is positive. We're not going to have any absolute values flying around with that x as being strictly positive. So in order to simplify this, let's remind you that we would write this as fifth root of x to the 15th is equal to b. This would convert to x to the 15th is equal to b to the fifth power. So then the question is, what to the fifth power gives us 15? And so this, we recognize this as x cubed to the fifth power is equal to b to the fifth power. So we have to get that b is equal to x cubed. So this is again assuming that x is positive. So the fifth root of x to the 15th is x cubed. But one thing to note is, isn't 15 divided by 5 equals 3? So if we could write x to the 15th divided by 5 for the fifth root of x to the 15th, we would immediately see that this is equal to x cubed without all of this drawn out work. And in fact, we can. So when the nth root of a is real, so the initial step is to determine if it's real or not. In our case, it will be. But when it's real, then we can write the nth root of a is equal to a to the 1 over nth power. So for example, the square root of 7, that's quite real. That's equal to 7 to the 1/2. We can see that 8 to 1 over cubed. Well, converting backwards, this would be the cube root of 8. That's quite real, which we've already seen is equal to 2. So this gives us a way to nicely simplify these things in a way that involves fractions and rational numbers. So we have a nice property. So for m and n being positive integers, with the nth root of a being real, we have a to the fractional power m over n is equal to the nth root of a to the m, which is equal to the nth root of a to the nth power. And another version is, for a is not 0, 1 over a to the m over n is equal to a to the negative m over n. So the basic idea here, if I needed to do 8 to the 2 over 3, this is looking a lot like the first one there. And so the question is, should I simplify it to the first one first or the second one first? So let's see here. So if I do the first one first, this is equal to the cube root of 8 squared, which is equal to the cube root of 64. Well, that's not super nice. But we know, in fact, that is, in fact, 4. But if we were to convert it the other way, say if we did 8 to the 2 over 3 is equal to the cube root of 8 squared, well, the cube root of 8 is 2. That's rather nice. So that's 2 squared, which is equal to 4. So choosing which version to convert it to really depends on what you're doing. I personally will like to convert it to taking the root on the inside and then exponenting on the outside, because taking the roots often makes the number smaller, so when you exponentiate it, it gets a little bigger. But if you do the exponential first, which is perfectly valid, often the number on the inside gets bigger, and then the root makes it small again. So it honestly depends on what you are up to. So let's work through some examples. So for the first one, I am going to do the fourth root of 25. So the first step here is I'm going to convert this into a fractional exponent. This is 5 to the 1/4 power. Remember, the radical goes in the denominator. But isn't 25 5 squared? So if I write this this looks like it's a 5 squared to the 1/4 power. Well, that looks pretty nice. So what if we could just multiply this and say that this is equal to 5 to the 2/4 power, which simplifies rather nicely to 5 to the 1/2 power. Well, that looks quite simple. So this is equal to the square root of 5. So the fourth root of 25 is in fact the square root of 5, provided these intermediate steps are true, which they are, in fact are. We'll talk about those in a moment. Next, let's try to do negative the fifth root of 32. So that negative is on the outside, which is completely fine. So this is a real number. So we can just keep going as usual. So I'm going to convert this to a fractional exponent. So this is negative 32 to the 1/5 power. I'm going to put parentheses there to indicate that we're going to just do the negative on last. But isn't 32 2 to the 5th? So this is equal to negative 2 to the 5th to the 1/5 power, which simplifies rather nicely to negative 2 to the 5/5. Well, that's just simplifies down to negative 2 to the 1. So I'm just going to leave it like negative 2. That's super nice. 3. How about negative 81 to the 1/4? Well, just looking at this, I'm looking at it and going like, okay, that's a negative and that's a fourth root. So let's just take a look at it as a radical. So this is the fourth root of a negative 81. Uh-oh. This is a even root of a radical. So this is not real. So that's not a real number. It's not a real solution. So the fourth root of negative 81, which is equal to negative 81 to the 1/4 power, is not real. I also want to point out that sometimes fractional exponents can hide non-real radicals, and some of the algebra that you can do only works provided everything is real. So you do need to double check before you do any of the algebra that the things are real, because it can pass from real to not real or not real back to real, depending on some invalid algebra in that case. All right, so 4. Let's see here. How about this one? Negative 64 to the 1/3. Well, just computing that, that looks awful a lot like the cube root of minus 64. So that's real. We're all set. So I'm just going to keep going with this. So 64. So 64 is equal to 4 cubed, because I'm looking for a cube root, so I'm going to say 64 is 4 cubed, but it's negative 64. So I'm going to say that this is equal to negative 4 cubed. We still have that 1/3 hanging out on the outside. So in this case here, this is equal to negative 4 to the 3/3, which is equal to negative 4. So this is when I say it can hide. So like for instance, if that inner 3 was a 2, that would hide the fact that we are in fact dealing with a real number or a non-real radical. So like for instance, if that was like a square root there and I ended up accidentally squaring or to the 4th power of the inside, it would hide that altogether. All right, so 5. Let's see here. Let's do one more of these. So what about 1/27 to the 2/3? Well, that's real. That's a cube root. The cube roots are fine. So the first thing I note is 27 is equal to 1/3 cubed. That's rather nice. So that's the 2/3. So this thing is equal to, I forgot to change the color on that. I'll just do that now. And so this thing is equal to, well, I'm going to take the cube root first. So this is going to be the cube root of 1/3 cubed squared, which is in fact equal to, well, the cube root of 1/3 cubed is equal to 1/3 squared, and so that's equal to 1/9. That's pretty nice. This is one of the cases where I'm like, okay, I'm going to take the root first and then square it. Because if I were to square the inside first, I'm not even sure what the square of 27 is, let alone 1/27. So that's why I wanted to take the cube root first, because that is very nice to compute. So let's consider some properties. So R and S be rational numbers, A and B numbers where the following are defined, so that we're not dividing by 0 or taking an even root of a negative number, so everything is real. So we have the first 7 properties being a to the r times a to the s is equal to a to the r plus s. Second, a to the r divided by a to the s is a to the r minus s. So these just mirror the exact properties here coming from integer exponents. If you have like x squared times x cubed, that's like x to the 5th, and x squared divided by x cubed is x to the negative 1. Same identical properties for all of these. So we have a to the r to the s is equal to a to the r times s. We have a to the a times b to the r is equal to a to the r times b to the r. That's pretty nice. A divided by b to the r is a to the r divided by b to the r, so this thing splits pretty nicely over division. And we have a to the negative r is equal to 1 over a to the r. And then we have a to the minus r divided by b to the minus s. This is the basic idea of flipping and multiplying coming from integer exponents. So we have a to the b divided by a to the r. So translating here 4 and 5 into radical notation, so provided the nth root of a and the nth root of b being real, the product of the nth root of a and the nth root of b is the product of the nth root of a times b, and the nth root of a divided by the nth root of b, provided b not 0, obviously, is equal to the nth root of a divided by b. So let's wrap this up with just a couple more. So how about a to the 1/3 b to the 3 over 2 cubed? Well, I just want to remind you that this just distributes in. So this is equal to a to the 3 over 3 times b to the 9 over 2. So this is equal to a times b to the 9 over 2. That's really as simplified as we can get that. B over to the 9 over 2 isn't the greatest thing here. 2. If we do a cubed b to the minus 4 divided by a to the minus 2 b to 1 over 3 to the negative 1/2. All right, so we're like escalating a bit here. So the first thing I'm going to do is simplify the inside. So the first thing I see here is that this is going to simplify down to a to the 3 plus 2 times b to the minus 4 minus 1/3 minus 1 over 2. So I simplify those fractions down by subtracting there. So this simplifies down to a to the 5. So that works out pretty nicely. And then negative 4 minus 1/3 is b to the minus 13 thirds. That's not the greatest. And then we have the minus 1/2 here. So that is going to be equal to, oops, sorry for the jump there, 5 to the, or a to the minus 5 over 2 times b to the positive 13 over 6. So this is equal to b to the 13 over 6 divided by a to the 5 over 2. No, that's not my favorite, but we did it. And then for our very last one here, the 4th root of x cubed times the 5th root of x. I'm just going to put a big old asterisk on this one. This one I notice a lot of issues with. So the first thing is you convert both to fractional exponents. So this is equal to x to 3 over 4 times x to the 1 over 5th. All right, so common denominator is 20. So this is equal to x to the 15 over 20 times x to the 4 over 20, which then just adds as x to the 19 over 20. So it's the x is the taken to the 19th power, then you take the 20th root of it. It's not the greatest. But this is honestly how you compute this. The biggest issue that I see is adding the 4 and the 5 to get the 9th root, and then adding the exponents here to get a 3 and a 1. So what I see a lot of students do is you get the ninth root of x to the fourth, and that is very much not the case here.